saying 10 minutes behind the schedule, so we are not getting later. Please.
Can you please go to the time evolution picture? Excited state and ground state.
Video?
Yeah. So what is the equilibrium position of excited state in here?
Equilibrium position for I use for both this 3.4 atomic units as the excited ground and excited state.
Let me reformulate Javed's question so that you answer it in a better way. Can you scroll back a couple of slides? More? Here. Okay, so for the excited state potential, is there an equilibrium position? You hear answer to your question? Okay. Other questions?
Because this is where the reaction happening, right? If it would be staying in this excited state, then it would be minimal, but it's really dissociated potential. That's why it doesn't have anything.
But if it's formed a product, so then they have a equilibrium point, right?
Do not ask me, ask him.
At the transition state is not, they have no equilibrium point, it's going down. But after then, they have
So after
equilibrium.
that it transforms to the excited state potential. It start with the ground state potential, and at ground state I use the carbon sulfur bond length as the equilibrium position, and with time it transforms to the excited state potential. At the beginning it stays at the ground state, and then it transforms to the excited state.
More questions?
No, I'm good.
Brief one. You are activating your reaction by heat, by kinetic energy.
Yeah.
Is it possible to use other forms of energy to activate the same reaction? Can you activate it by anything else? By light? By voltage?
So in this method I change the initial momentum of the wave pattern. So
But from your experimental background, can one
from
activate
experimental, so this thiophene hydrogen desurfurization require high amount of energy. It require elevated temperatures like 570 to 700 Kelvin. So I don't think we can do photoexcitation because we are doing bulk reactions. So from my knowledge, I don't know about anything like in photoexcited reactions for hydrodesulfurization. So I'm not sure about that.
Okay, last chance. Please. Professor.
In this Arrhenius the plot you were showing, actually you were showing this the linear trend, right? But
Yeah,
if you take a look at the points, actually it goes to
The
the
red
flash,
one.
right? It's the relationship is not non-linear actually. When you change when you increase the
Initial kind
the energy, the electron transfer rate actually gets to flat point. You see, it's not changing actually at the end, right? So it's not so linear.
So maybe it's second order reaction.
Actually,
just
same thing happened in my data. If I draw their exponential graph, it exactly matches the exponential.
yeah.
So
it's kind of
in a
more
particular
exponential.
range, it obeys that Arrhenius relationship. So I use I consider the activation energy of the carbon sulfur bond breaking of thiophene. So I consider the activation energy of the whole thiophene hydrodesulfurization reaction as the activation energy, and I measure the use the activation. I change the activation energy from 0 to 2 times of this real activation energy. So in a particular range, it obeys this linear relationship, and if I increase the activation energy for a larger value, like 3 times larger than activation energy, then it stays like a constant.
Yeah,
So I have that kind of a trend. Yeah.
Okay.
Okay, please join me in thanking